Okay, we're starting. Okay, so showered, rested, Saturday. We can start 4.4 now. Hopefully, not going to make as many mistakes today. So, section 4.4 is all about one thing and one thing only, L'Hopital's rule. What's L'Hopital's rule? Okay. So we're going to have two functions that are divided by each other, right? And we're going to take a limit as x approaches some constant a or infinity. Okay. So what we'll often get is if we sort of like plug in a, or if we take the limit as x approaches a for both of the functions like we normally would, like we would in, like, say, chapter 1 when we were first learning limits, this would go on to be of the form either 0 divided by 0 or infinity divided by infinity. These are two indeterminate forms. Basically, we can't look at these and say, oh, this limit does exist and it goes here, or this limit doesn't exist. We don't know that. Doesn't matter what the functions are. We can't look at these and tell. What L'Hopital's rule tells us, though, is if these two functions are differentiable around a and g in the derivative of g of x and g of x and the derivative of g of x don't equal 0, then this limit, the limit we start with, is going to be equal to the limit as x approaches a of the derivatives divided by each other. The derivative of f divided by the derivative of g. This is basically L'Hopital's rule. If we have one of these, the 0 over 0, infinity over infinity, we can't tell if the limit does or doesn't exist, but as long as our functions are differentiable and the derivative of g of x doesn't equal 0, is it? Actually, no, not even that. Actually, yeah, just derivative doesn't equal 0, then this limit equals this limit. So generally, just erase all the theory, all the like the formalness. If our limit is a 0 over 0 or infinity over infinity, take a derivative of the top, take a derivative of the bottom, take the limit again. That's basically what we end up doing with L'Hopital's rule for Calc 1. I'm going to show you some examples. Okay, here's our first example. We want to take the limit as x approaches 3 of this fraction, x minus 3, divided by x squared minus 9. First, let's just see where this goes. We're going to take the limit as x approaches 3 of both of these. Three minus 3, that's going to be 0. X squared minus 9, 3 squared minus 9, that's going to be 0. We have a 0 over 0 indeterminate form. So, let's do L'Hopital's rule. Our new numerator is the derivative of our old numerator. Derivative of x minus 3, that's 1. Our new denominator is the derivative of our old denominator. Derivative of x squared minus 9, 2x. We take the limit of this, we get 1 over 2 times 3, 1/6. That's L'Hopital's rule in a nutshell. We get an indeterminate form, take derivative of the top, take derivative of the bottom, take the limit of that, and we should get 1/6. If you graph this out, you'll see that the two sides do end up meeting at about 1/6. Also, worth noting is you don't even need to apply L'Hopital's rule to this problem. Something you could have done, and that kind of confirms this works, is we could have factored the denominator, canceled the whole. We take the limit as x approaches 3 of 1 over x plus 3. That's 1/6. So, you can do it either way in this case, but it confirms the limits are equal. Let's do another one. Okay. Problem 2. We're taking the limit as x goes to 0 of the tangent of 3x divided by the sine of 2x. What's this look like first? Well, if we take the limit of tangent of 3x as x goes to 0, that's the tangent of 0. Tangent of 0 is 0. Similarly, we take the limit of sine of 2x as x goes to 0. That goes to sine of 0, 0. Indeterminate form. Let's take a derivative. Both of these are going to be chain rules. Derivative of the tangent of 3x is going to be 3 times secant squared of 3x. And derivative of sine is going to be 2 cosine 2x. Okay, so what's this going to be? If we take the limit of secant squared of 3x as x goes to 0, that is going to go to 1. Why? Because secant is just 1 over cosine, and cosine of 0 is 1, so 1 over 1, 1. Same deal over here, cosine of 2x, that goes to cosine of 0. Cosine of 0 is 1. 3/2 is our limit. Pretty much it. Let's do another. Problem 3, same as the first two. We're taking the limit as t approaches 0, and we're taking the limit of 8 to the t minus 5 to the t divided by t. Well, if we plug in 0, what do we end up getting? We get 8 to the 0, which is 1, minus 5 to the 0, which is 1, all divided by 0. 0, 0, 0, zeros across the board, indeterminate form. L'Hopital's rule, we're going to take the derivative. Denominator isn't too bad. Derivative of t is 1. Derivative of 8t, well, that's 8t times the natural log of 8. If you remember, our derivatives of not logarithms, exponentials. Our derivatives of exponentials. Derivative of 5t, well, that's 5 to the t times the natural log of 5. And if we take the limit of this as t goes to 0, we get 8 to the 0 times the natural log of 8 minus 5 to the 0 times the natural log of 5. We get the natural log of 8 minus the natural log of 5. And if you want to simplify it a little bit more, you could even write it as the natural log of 8/5. This is the procedure every time we have a fraction one. If you see a 0 over 0 or an infinity over infinity, derivative of the top, derivative of the bottom, take the limit of that, and there you go. Okay, so we've done enough fraction ones, let's do a product. Okay, so for one of the problems, I accidentally typed it up wrong, so I've been a little bit rushed. I would like to apologize. We're taking the limit of x to the 3/2 times sine of 1 over x as x goes to infinity. Not 0, infinity. Well, the x to the 3/2 is obviously going to infinity as x goes to infinity. And the sine of 1 over x, that's going to sine of 0, which is 0. This is a product indeterminate form. If we have a limit that's like a 0 times infinity, we can't tell if the limit exists or not or what it's going to. That's a problem. Sorry, someone's revving their car up the road. What do we do though? Well, here's what we can do. We are going to rewrite this limit as follows. We're going to have sine of 1 over x, and we're going to have 1 divided by x to the 3/2. We're going to write it like this. We're going to switch it around so we have 1 over x to the 3/2, or alternatively, x to the negative 3/2 in the denominator and sine of 1 over x in the numerator. Why are we doing this? It makes this a fraction. Turning one of these into dividing by a reciprocal makes this a fraction, and if we apply the limits as x goes to infinity, we see that they both go to 0. This is a 0 over 0 indeterminate form. So to this problem, we can apply L'Hopital's rule because of that 0 over 0. Let's do that. Derivative of sine of 1 over x. Well, derivative of the outside, we're going to have cosine 1 over x. And we're going to multiply by the derivative of the inside function. That's going to be negative x to the negative second. Yes. And down here, we're going to take the derivative of this. We're going to have negative 3 halves, x to the negative 5 halves. And we're going to take the limit of these as x goes to infinity. So, apologies, just had to check something real quick. If we look at the limit as x goes to infinity, we get cosine of, this is going to be 0, so that's 1, times negative x to the negative second. If we plug in that x to the infinity there, that's going to be a 0. So that's 0 in the numerator, and we also get a 0 in the denominator. Are we going to apply L'Hopital's rule again? No. Here's something we can do on occasion. Notice that we have a negative x to the negative second up here and an x to the negative 5 halves down here. Sometimes, if we can, it helps for us to rewrite our functions so that the limits become a little bit more calculable. So the negatives are going to cancel out. Just 3 halves. We're going to bring it up out of the denominator. It's going to be a 2/3. X to the negative second minus x to the negative 5 halves, negative 2 plus 5 halves. This is going to be square root of x. And where does this go to? Well, that cosine of 1 over x, that's going to 1. That square root of x is going to infinity. We're going to infinity. So that's something to keep in mind. L'Hopital's rule can let us evaluate complex limits, complex product limits, but sometimes you should keep in mind that cancellation, instead of doing L'Hopital's rule again, can be helpful. Why don't we do L'Hopital's rule here? Because we're never going to stop doing L'Hopital's rule. We take a derivative, it's always going to be a 0 up top, because our x is going to infinity, we're always having x's in these denominators. Denominator, it's just going to keep getting more and more negative exponent. That's going to go to 0 too. We're not going to stop, so writing it like this is pretty helpful. But keep in mind, key thing here, when we have products that have a 0 times an infinity, we can rewrite them in such a way that we get an indeterminate form upon which we can apply L'Hopital's rule. Let's do another one. We went through an example like this in class, but let's do it anyways. X cubed minus e to the negative x squared. Well, if we apply this limit, we're going to end up getting the x cubed going to infinity and the e to the negative x squared is going to 0. Indeterminate form. Let's rewrite it. This one's pretty easy to rewrite because of that negative exponent. This, if we apply the limit, we get an infinity over infinity indeterminate form. So we can apply L'Hopital's rule to this fraction. Derivative of x cubed, 3x squared. Derivative of e to the x squared is e to the x squared times 2x. And if we do the limit here, if we apply the infinity, then we get this is going to infinity and this is going to infinity too. So that's an indeterminate form. We could keep taking the L'Hopital's rule, could keep doing the derivatives, we'd have to do some product rules, or we can do this real quick. (3x over 2e to the x squared). This is still an infinity over infinity indeterminate form, but taking the derivatives of these is going to be a lot easier. If we take the L'Hopital's rule again. Derivative of 3x is 3. Derivative of 2e to the x squared is 2e to the x squared times 2x. Numerator is going to be 3. Denominator is going to infinity. This limit's going to 0. I know I talked to you all in class about just sort of like iterated, just saying, oh, we can just keep applying L'Hopital's rule, a polynomial will just disappear. But you can also think about it as just we're canceling some terms out, and that often makes our L'Hopital's rule easier to deal with. So that's two different ways you can think about a problem like this. So products, again, rewrite as a fraction. So it's 0 over 0, infinity over infinity. Apply L'Hopital's rule to that. Let's do another one. This time we're going to do subtractions. Here's a problem. We're taking the limit as x goes to infinity of x minus the natural log of x. Okay, so what's the big deal? If we break up this limit across that subtraction sign, then what we end up seeing is these are infinity minus infinity. So this is an indeterminate form for subtractions. What are we going to do with it? Well, we can't tell where the limit's going because we don't know which one's getting bigger faster. We don't know which one wins the competition. So we need to find a way to rewrite this as fractions. Now, a lot of the times for L'Hopital's rule, you'll see two fractions, and they'll be going to infinity and infinity. For that one, solution's pretty obvious. Just give them a common denominator, combine them together, and apply L'Hopital's rule on whatever the hell remains. This one, however, is a little bit different because these aren't fractions. What do? Answer is you're going to want to factor out one of the terms. So let me show you what I mean by that. Let's factor out x. If we factor an x out of both of these terms, we factor an x out of x, that's 1. We factor a natural log of x we factor an x out of the natural log of x. Like that. Okay. Where's this going? Well, we know this x term here is going to infinity, but we don't know what this term here is going to. Because, well, it's an indeterminate form. If we applied the limit x to the x going to infinity here, we'd get infinity over infinity. That's not good. But we need this fraction. We need to know what this goes to as x goes to infinity to evaluate this whole thing. How do we find it? L'Hopital's rule. Natural log of x over x, we take a derivative. So we get 1 over x divided by 1. Long story short, this goes to 0. So what does this function go to as x goes to infinity? This x term goes to infinity. So let me box this off a little bit. The x term goes to infinity. The natural log of x over x term goes to 0. We have infinity times 1. So what's infinity times 1? Infinity. Like it's not times 0. Anything times infinity is infinite. So this limit is going to go to infinity. That's our answer. Another way you could think about it, x goes to infinity, x gets bigger faster than the natural log of x. Good Lord. I'll be right back. Okay. Whenever you see subtraction, if it's two fractions, give them a common denominator, combine them, apply L'Hopital's rule like normal. If you see things like this, what you're going to do is you're going to factor out one of the terms, and whatever fractions remain, you're going to apply L'Hopital's rule to those to evaluate those limits. You could have also just as easily factored out natural log of x from both of those, and that would have been totally fine. You would have gotten the same infinite limit. Doesn't matter which one you pick. Last up, I'm going to show you an exponential. All right, we're taking the limit as x goes to infinity of x raised to the power of 1 divided by x. What happens if we take a look at these limits separately? We get infinity over 0. That's an indeterminate form. There's 3 indeterminate forms for things like this. If you have a function raised to the power of another function, you have an indeterminate form if any of the following are true. Infinity over infinity raised to the 0, 1 raised to the infinity, and this last one was 0 raised to the 0. That's it, yeah. So for any of those 3, you're going to apply the following technique. First, we're going to give a variable y, and we're going to set it equal to what we're trying to find the limit of. Basically, we're trying to find the limit of y, right? Okay. Now here's what we do. We're going to take the natural log of both sides. And what does this allow us to do? We're going to be able to move that exponent fraction down in front. Okay. So we have 1 over x times the natural log of x. How does that help us? We're going to take a limit. We're going to take the limit as x approaches infinity of natural log of y. We're going to take a limit as x approaches infinity of that 1 over x natural log of x, or natural log of x divided by x, right? So this is an indeterminate form in fractions. This one's a product, this one's a fraction. They're still indeterminate forms. Infinity over infinity, right? We actually did this one for the last problem. If we take the derivative of the natural log, we get 1 over x. Take the derivative of x, we get 1. We're just taking the limit as x approaches infinity of 1 over x, which is 0. Okay. So what does the natural log of y go to as x goes to infinity? 0. Okay. But that's not what we're looking for, is it? We want the limit as x approaches infinity of normal y, of x raised to the 1 over x power. So, if natural log of y goes to 0, how do we undo natural logs? We raise it to the power, we raise them as powers of e. If the natural log of y goes to 0, e to the natural log of y is going to go to the e of 0. Or, y is going to e raised to the power of 0, which is 1. Y goes to 1 as x goes to infinity. Apologies. X raised to the 1 over x goes to 1 as x goes to infinity. How do we find this? We take the logarithm of it, we resolve the limit of that logarithm changed form, and then we undo the logarithm by making it a power of e. There we go. And you can do that for this one, or this one, or this one. They're all fair game. Let's see. Yeah, I think that's about it for L'Hopital's rule. Yeah. Just rewrite as a fraction and take derivative of numerator and denominator, and do not, under any circumstances, apply the quotient rule to the fraction you're trying to find the limit of. Gonna throw that in there. Okay. I'm gonna wrap this up, and then we're gonna get started on 4.5. That's curve sketching.